Okie dokie. Let's see. Okay, I'll get moving here in a minute. Actually, here, let me put that over there so I can see the clock. There we go. Okay. Yeah, I'll get moving here in just a minute. Let a few more people stream in. Before I get moving, like usual, any questions anybody has? Assume my mic's working. Yeah, I can see it's picking up. All right.
I have a question. So I am trying to use the cat function and piping it into an object I've created that has a vector of variables, or not variables, a vector of elements. And then every time it prints, it repeats it over and over again. Is there a way to stop it from repeating over and over again?
So do you have an example code for?
Yeah, it's for my other class, but I'll just put it in here.
Okay. So. Okay, I see. Okay, so. So ABC is a nice character vector. Let's see, you're just going to go sequence along that, apply through that, paste. Okay, yeah, that should repeat it a whole bunch of times. What are you trying to do?
Only trying to get a response where, oh, I see what it's doing. Okay.
Yeah, it's essentially, so this right here, right, is a vector 1, 2, 3, 4, 5, 6. What sapply is doing is it's running through, it's going to run this 6 times. It's going to run it once for each of these numbers, but it's not actually using any of these numbers. And because it's doing that, it's just going to repeat this paste operation 6 times.
Okay.
Yeah.
If I wanted it to just do it once, I would get rid of the sequence along and just put ABZ instead of going column by column.
Oh, so you want to come out as a, what do you want to come out as?
Just as a paragraph, like with all those things, with the returns in those spaces.
Oh, yeah. The easiest thing would be collapse like that. And when that prints, if you ran it as actual text, it'll do line breaks.
Okay. Okay.
Yeah. So collapse here, what it says is instead of basically pasting this onto each one of these elements, but leaving it with the same length, collapse says reduce it down to a length 1 vector where it's divided by these.
Okay. All right. Thank you.
Yep. We'll do that. Week 7 a bunch. Okay. Okie dokie. So I will get moving. I didn't see anybody else that's put anything else in chat. We got a pretty good number of people in here.
I have a question.
Oh, yeah.
So I can't remember if it was you or the other R lecture that I'm going to right now, but somebody made a really casual reference to, like, if you start your scripts with, you know, whatever you use to clear the workspace, like RM equals LS or whatever.
They'll burn your house down?
Yeah, was that you?
No, but that's a common thing.
So in MATLAB, you always clear your workspace. Why don't you do that in R?
Okay, so the idea is that if you have a script or a file that you want someone else to ever use, and someone else includes future you, it's not a good idea in a language like R, where you might have many different things loaded and running, things that may have taken hours to generate, to begin a script by clearing those things. And the idea is that really the best practice for that sort of thing is you should be, if you have something where something should be running in total isolation, it should be running in its own RMD or its own project or something like that. And you should divide those things up because they already run in their own environments. Basically, I mean, the way I have, like the way you should have your RStudio and stuff set up is with, in here in the general tab of your RStudio options, you should have it set to not restore your R data into workspace at startup and never save your workspace to R data on exit. And if you have those settings set, every time you close RStudio and open up again, nothing gets reloaded into your environment. Everything is completely reset. So you should be doing that already. Usually the need for, so the clearing command is rm list equals ls, which says I'm going to remove a list of crap. The list of crap is ls. ls is just everything currently loaded in your global environment. The other thing about rm is rm list equals ls is these are the only things it's going to remove, the things up here in your global environment. It doesn't clear loaded packages and stuff. So it's not even clearing your environment fully. It's one of those ones where it deletes only these things you see up in your global environment, but every package I have loaded is still loaded right now. So it doesn't actually cleanse your environment anyway. It's sort of lying to you, but it is a good way to kind of just get rid of some things. But in general, it's the type of thing you only do in your console because you want to like clear everything suddenly, but you shouldn't begin scripts with it because if your scripts are dependent on things loaded in the environment to begin with, you're doing something wrong and they shouldn't be containing anything dependent at all. In other words, the source of that, if you begin your script with rm list equals ls, I'll burn your house down, is Jenny Bryan over at UBC, one of the greatest R and RStudio instructors. And she's like, in her Stat 545 class, she's very much like, there's all these practices and things you shouldn't do. And much of my advice in this class is based off of her advice, which is really some of the best out there for workflow and project management. Generally, she says something to do something, she's probably on target for, that sort of thing. Okay.
Awesome. Thank you.
Yeah. Okay. So today we're going to move away from nuts and bolts again and back to more abstract things, but abstract things that are useful. That's that's Jenny Bryan. So I'll type it in chat. Jenny Bryan, she's a professor at UBC, teaches their main R class up there in the statistics department, and she's also one of the core people in the Tidyverse in RStudio, one of the best people for R education, and also is a developer in many of the key packages. So just a key person in the world. Okay, so today is going to be about importing, exporting, and cleaning data with special attention paid to pivoting your data between long and wide formats. So practical stuff you probably will deal with a lot in your average project. Okay. So the general theme for today is what I would call data custodian work. This is sort of the kind of work you need to do to get your data in, clean it up so it's ready to go, and do analysis with it, and also have it prepped to be able to send it back out to other people. Sort of the drudgery sort of work that lets us do our analysis, our sharing, and sort of make our data usable. Okay. So things I'm going to talk about include working directories and projects, importing and exporting data using Reader and Haven, cleaning and reshaping data using TidyR, and then I think I'm going to finish off, with dates and times with the LubraDate package. Dates and times are a weird data type, and so you kind of need special tools to work with them. And I've got a little bit on factors in here using the 4cats package that will hopefully demystify some of the reasons for using factors. Okay. So first thing I want to talk about is directories and working directories. This calls back to, I talked about them a little bit at the beginning of the week 2 lecture on saving and loading files. Okay, so you might recall that the working directory is where R looks for and saves things sort of by default, okay? You can find where that is using getwd. If I ran getwd, for instance, I ran it when these slides knitted earlier today, my working directory for these slides is here. It's on my C drive because I'm a Windows person. Users, me, my OneDrive, my GitHub, this class, lectures, and this particular lecture. Okay, my working directory is nested all the way deep in here. and that's where it's going to look for files. Okay. So if you want to set your working directory, which is generally inadvisable, but I still show you how to do it, you can just say set WD and give it a new path, okay? This will change the working directory to that location. It will save files there. It will load files from there, okay? My recommendation is basically you really should never have to change your working directory if you're doing it right. Suggestions are if you're using an RMD file, RMD files use their current working directory or current directory as a working directory to begin with. If your RMD needs something, just put the stuff in that folder or in a subfolder or somewhere relative to that location, and you'll be good and you'll have to set working directories. For big projects, instead of setting them, you should probably use RStudio projects to manage them. Do I have something on the here package? No, I don't. Another thing you can do to manage your directories is this package called here, H-E-R-E. Here does basically the same thing as RStudio projects, but doesn't require RStudio. It's another way to manage your working directories automatically. Something to know, if you copy a path from Windows Explorer, so Windows Explorer just being any window you open up on Windows, Windows is a dumb operating system. So when I say it's a dumb operating system, I mean that, let's say I go to CSSS508, I go in here to maybe the homework directory. If I go here to my directory location, you'll notice that the slashes in Windows go the wrong direction, okay? This is because Windows has inherited the dark legacy of DOS instead of Linux, and they decided that you should use this type of slash instead of the other type of slash. Okay, so if you want to copy and use this directory in R reserves these backslashes like this for escaping characters. You have to flip all these slashes the other direction if you want them to work, okay? Just a heads up. If you're on a Mac or some other Unix derivative operating system, you don't have to worry about these things because it was made by, well, I'm say it's made by non-idiots, different idiots with a better standard. Okay. Now they're all brilliant people. Windows 2, actually. Okay, so if you need to set a working directory, put setwd at the start of the file. So 98% of the time you shouldn't be setting your working directory, but if you have to, put it at the top at least so people can see your transgression and fix it when they load it on their computer, because your working directory on your computer will never work on someone else's computer. So yeah, put it at the top. Okay. So a better way to deal with working directory is to use the project feature in the top right of RStudio. When I say in the top right, up here is the project functionality in RStudio. Like right now, I'm loading the CSSS508 project, but I can load all sorts of other projects here and just flip right to them, okay? That's project management. Okay, so this project management has a lot of advantages. One big one, it deals with working directories. If you have a project set up, your working directory for everything you're using in that project will be set to be the root of the project directory. It also remembers objects in your workspace, your command history, etc. the next time you reopen that project. You reopen it, everything you were doing is there, so you don't have to worry about like keeping a bunch of random things from different projects in your R at the same time. You can keep a nice clean environment, just move between different projects. Another one is that it reduces the risk of intermingling work between projects. One of the most common things that I used to have to troubleshoot for people when I was working down in the Caesar lab, that's a consulting lab on campus, is that people would come in and not be able to run some script that worked for them a little while ago. And usually what it was is they were working on a homework for one class that used some common variable names like X and Y that they then needed to use in some other file. Because they'd overridden it when they ran that script, it didn't work on the other script because they just had all their stuff open in one instance of RStudio. This is always a bad idea. You should really have everything as separate as possible. Another thing with projects is projects integrate with version control systems. So if you get a little more advanced in this stuff, you start hosting your stuff on GitHub or whatever, use Git for version control. RStudio has a nice Git handling up here, so you can actually do version control up here in a Git panel in RStudio. Your entire project will be a repository, say on GitHub. It's a nice way to sort of handle things. I actually don't use this functionality for a couple reasons, but a lot of people I know do. Okay. Yeah. So as one thing, I usually make every one of my RStudio projects a different GitHub repository. If you do use GitHub, I mean, you go on my GitHub, you'll see I've got a million different repositories for different things. This class, for instance, is a single GitHub repository, and the class is hosted on it. But things like my curriculum vitae is like a GitHub repo, whatever you want, GitHub repo. Sometimes journal articles will be a repo too, and they are also just a project. If you're interested in more advanced project management stuff, you can ask me about it later or in lab, or you could check out, I have sort of a somewhat dated presentation on reproducible research using RR tools. I will cover some of that stuff in week 10. So let's see. In chat, for one class I have, every homework, lab, etc. has its own R project. This has made it a mess of R project in my folders. Can I delete the files and still use the RMD and R files in those folders? Yeah, the R project file, you delete it, you can't the project goes away, but none of the files do. The R project is just defined by that one.rproj. This is the reason I don't make every single homework its own project. I usually make the overarching class or something the project, because he doesn't have too many of them, it's not necessary. Like each chapter of my dissertation is a project, but not each sub-analysis or something in that chapter. Okay, so once you've set a working directory or you're in an RStudio project, you can refer to files and folders within the working directory using relative instead of absolute paths, okay? What are relative paths? So if I do something like load up ggplot, do a quick little plot here, a plot, and I want to save it, but I don't want to save it in the same directory as these slides. Instead, I want to save it in, say, a folder called graphics. I can say ggsave graphics folder cars plot png. So you can give paths here. As long as there's a folder called graphics in the same folder as your RMD, it will browse into that folder and save it there. This is called relative paths. It's relative because you're not specifying the exact drive on your computer that it is, or the exact sort of directory. It's just saying it's relative to your current working directory. Okay, so that would just save it in that graphics directory. Okay, so relative paths are nice. One of the reasons is because all the locations for your loaded and your saved files can be changed just by changing the working directory. This is nice because you could do something like pick your entire project up, the whole project, drag it somewhere else on your computer or onto a flash drive, hand it to someone else, and all those directories go with it. And so the paths also go with them, and people don't have to go in and change every single path from C:/whatever. Instead, you can just move it wherever you want, everything works. A great question here in chat is, can you go up the level with relative paths? It's not a bad practice. I do it all the time, and sometimes there's good reasons for it. A good reason for it is, for instance, my dissertation uses the same data for basically at least the same data sets in all three of the chapters, some of them shared, so I don't want to just replicate the data across them. Instead, it's in a top-level data directory. If you begin your path here instead of graphics like this, if you did period, 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 period will go up one directory level. And you can see this in RStudio. So if I say like, I think ls takes, okay, no. So what is it? It's list.files. List.files is looking in my current working directory. If I say list.files, period, period, that's everything inside my GitHub repository, my GitHub directory, one directory above my CSSS508. So period, period browses up, and you can keep browsing up repeatedly. So this browsed up one directory and then another directory. Okay. So, yeah, you can do that. Okay, so that's all I want to say on directories. If anybody has any questions on that, let me know. Otherwise, I'm just going to jump on to importing and exporting data. Okay, so importing and exporting data. So first thing, if you're working with a relatively popular data source, I recommend you try Googling first to see if it has a devoted R package somewhere to pull data off of it. There's a lot of sort of common data sets out there that have some package that'll grab it for you. For instance, there's like World Bank data, World Health Organization data. One we're going to use in week 9, which is Tidy Census for getting census and American Community Survey data. I haven't used QuantMod myself, but it's financial data from a variety of sources. Kieran Healy has a package for the General Social Survey, GSS package and stuff like that. A lot of these common data sources have a package. So instead of going and downloading their CSV files or Excel files or Stata files or something, you can just pull them straight down into some nice, often tidy format in R and not deal with like manually grabbing things. That's a much better way to grab data than doing everything manually. Okay. So if there isn't a package for the data you're working with, the next easiest way to work with external data is if it's in some delimited text file. Delimited text files are just text files where each entry, each value in them is separated by some uniform character. The most common are comma separated values or .csv sheets, often popped out of Excel or put into Excel. A CSV looks like this. CSV is comma separated. So this is a value. The comma says that's the end of that value. The next thing is a new value. Here's another value. They're all separated by commas. Full rows in the data are separated by line breaks. This is a CSV file. You'd load it with CSV related commands. Sometimes you'll see TSV or tab separated files. They're out there too. Sometimes you see really weird stuff like colon separated values, double slash separated values, space delimited values. There's a lot of stuff out there. There's also fixed width format files, which are really common if you're working with stuff that used to be on punch cards. So if you're working with data from like the 1970s or 80s, it's commonly something like every row is 80 characters wide. That's punch card data. If you get that, you'll be looking for fixed format data, which I don't talk about in this class because it's kind of uncommon nowadays, but I've had to work with a lot. If you got questions, let me know. Okay. So R does have built-in functions for importing text data, that is CSVs and TSV files. Those functions include read.table, read.csv, and so on. I recommend not using them. I would instead recommend using the ones in the reader package, which is the tidy versus like text reading package. These include read_CSV, read_TSV, read_delim, which just is a general one that lets you pick what delimiter to use. So there's some nice features in this. One is that reader does tend to be substantially faster than the base R ones. Not always, but it is faster. If you need a lot of speed, I'm going to talk about a very fast package in a minute, but reader tends to be fast enough for most people. Once you have millions and millions of rows, it can be a little slow. Another thing, it has better defaults. This second statement here I actually forgot to remove and isn't true. Up until R 4.0, the base R ones would convert all character, all string data to factors. They don't do that anymore, which is nice. Something that reader functions are good about is that they automatically detect date and time data and convert them to dates and times, which is kind of nice. It does a good job with it. If there are errors in loading it in, there's a function in Reader called problems, and it will tell you what issues there were reading the data in to make it clear how you can go and fix these things. This is nice because the base R versions won't usually tell you. They'll just kind of screw up your data and not warn you, and you might not know for a while. Reader tends to let you know. And for large files, it gives you a loading bar, so you know it hasn't just crashed and died. If you use read.csv to load like a gigabyte CSV file, it just sits there. You don't know what it's doing. It might be thinking, it might be crashed. Reader at least has a loading bar. Okay. If you need a lot more speed, I'm going to mention in a minute the Vroom package. The Vroom package is ludicrously fast for loading CSV files, but it's a little bit more bare bones than Reader. Okay. So here's an example of loading in data that we're going to use for examples today. So we're going to load some data about song ranks from the Billboard Hot 100 in the year 2000. So I'm going to create an object called Billboard 2000 raw. I'm going to assign to it a read CSV. And notice this, the reader read CSV type functions can load not just a CSV file off your computer, but they can actually browse online and go and grab a file off of a website for you. So I can just punch in the web address for this Billboard CSV file on my website, and it will run and download it for you. You don't have to worry about going and downloading to your computer or something. You can just go grab it right off the website. Now, a thing that Reader will do when you load something in with Read CSV, it will spit out a whole bunch of information. This is telling you how it decided, based on how the data look, to load in the different columns in the data. So in this case, it said, okay, here's how I'm going to load everything in. .default says the default columns are going to be assumed to be doubles. Okay, good to know. The artist column loaded in as character data, so did track. The time column loaded in as a column time format. It recognized it as time data. It still is going to show up as character, but it formatted in a particular way. It recognized that the date entered column in here was date data, and it formatted as dates. And then there's a bunch of other things saying, well, these week 66 through 76 columns it loaded here as logicals. So for some reason, these came in as trues and falses. Because these are rankings, they're probably supposed to be numeric, and I'm going to talk about that in a second. But the general idea is that you can load in data and it will kind of give you a diagnostic breakdown of how it decided to load everything in the data set in to let you know what it decided to do. Okay, this is kind of nice. You don't need it, and you could specify these things for it if you want, but by default, it tends to be pretty smart. Okay, so if I look at the data types for the last columns in this, like I said before, it said week 66 through 76, loaded in as logical. What's up with that? So if I look over here and I get structure on the Billboard 2000 raw data set, and I look at the columns from 65 on, this is a big data set. It's got 80 something columns, right? I look at this and we see that, okay, it's a tibble. That's what it's supposed to be. 317 rows, 17 columns, because I've subset down to 17 columns. The columns for week 60, 61, 62, 63, 4, and 5 have loaded in as numeric data. We haven't looked at these data yet, so we're not sure if this is reasonable, but the general idea is if you have a bunch of columns that probably store the same data, week 60, 61, 62, and then suddenly at week 66, they start loading in as a different data type, something probably went wrong, okay? This is a thing that has to do, well, has to do with two things, actually. One is that if you have a very large CSV file that you read in with Reader, Reader will only glance at the first 1,000 rows of data to guess the column types to load things in as. So here's a question. Can you say what column double means again? That means Reader loaded it in as a double precision floating point number. Double is the default numeric data type in R. If something has a decimal place, it's probably a double. In fact, I'm trying to remember what the other thing that can have decimal places is. It's almost always a double. Double precision is very precise decimal points. Okay, so basically, Reader looks at the first 1,000 rows of your CSV and uses that to guess what to type all your different columns. The thing is that there aren't many songs, and as we'll see, there aren't any songs that were in this data for more than 60 weeks, okay? And so it's weekly columns of data. Because there's no data in the first 1,000 columns or first 1,000 rows for any of these columns, Reader is just like, I got no idea what's in there. I'm going to default to logical data, probably because it's all missing, right? It just makes it all missing, makes it logical. This is a thing Reader will do because it guesses for you, which is usually a safe thing to do. But if you have really sparse data, if you have thousands and thousands of rows and you have many columns that are like completely empty except for a few rows, this is a thing that might occur for you, I should say. Since it encountered no values, it assumed these columns, actually, I say it assumed they'd be character, but nowadays it assumed that they're logical. You could specify the column types manually to fix this problem. So instead of allowing Reader to guess what all these different columns are, I could specify that I want certain column types. So here what I do is I come up with a specification of column types. I'm going to show you what this is in RStudio. So Basically what I said here is I'm going to paste together a vector of ICCC capital D, repeat I 76 times. You're like, well, what the hell is this? If I display it, this is ICCCD 76 I's. Well, this is the way a reader takes column specifications. This says the first column is integer, the next three are character data, the fourth column is date, capital D, and every other column I expect to be integer data. Okay, so there's that many columns in the data set. I'm manually specifying them. Will you ever have to do this? It's entirely possible you will not, because Reader's pretty smart, or you might use another package to load things. But should you ever have to do it, you can steal this code in this example, modify it for your purposes, and load your data. Okay, so all that's doing here is I take that vector, a length 1 vector of column types, and I say read CSV, the same file, but I add an argument. The column type should be the same as those types I just generated. This loads in the data and makes sure it loads in as the correct column types. That's all I'm doing. Okay. Another thing that you could do, you could also adjust the maximum number of rows that Reader uses to guess the column types. Maybe I have 5,000 rows in the data. I could just say, read CSV, the file, look at all 5,000 rows. So guess max 5,000 says the maximum number of rows to read to guess what to assign the data types is 5,000 rows. You could just increase the number, right? Might load in better that way. I'm lazy, so I usually do that if I'm just working some data set quickly. Another thing you could do is you could use read.csv in the foreign package. This is the base R one. The reason Reader is faster than read.csv is because of this guessing thing that it does. Read.csv doesn't do any guessing at all. It reads every single row and then assigns the data types. It's slower, but it means it doesn't make any mistakes. Another alternative that you could do, which is a completely different approach, is to use Vroom. Vroom is a tidyverse package for high-speed reading of text data like CSVs. Vroom is very fast and very smart. So with Vroom, you just say, use the Vroom package to run the Vroom command. You notice here it's not Vroom CSV or TSV. Vroom is smart. Vroom will look at the file that you give it, detect what the delimiter is, and load it. Vroom is horrifyingly fast. It will instantaneously load CSV files in the gigabyte range, basically. And it does so through a lazy loading system that's technically complicated. If you got big files, like I was loading a terabyte set of CSV files on the terminal server a while back, Vroom is real quick, okay? The thing is, though, is Vroom has less error checking than Reader, so it doesn't give you those nice warning messages and stuff, which is a limitation. But there's one really cool thing Vroom can do Reader cannot do. Instead of giving one file name to Vroom, you could give Vroom the path to 100 different files. It will read all of them in sequence and knit them together into a single data frame automatically, which means you no longer have to loop over things or lapply or anything like that. It can read every file simultaneously, but it knits them all together into one data frame. If you've got a big data set split into like 1,000 different files, just say read the entire directory. It'll stitch them all together. One. Super nice. Okay, here's a question in chat. Sorry to go back a bit. You said since it encountered no values, Reader assumed they'd be character to be sure nothing would be lost. Yeah, it assumed to be logical. They changed that. So it used to be character the last time I revised these slides, and they changed it to logical if they're all missing, which makes sense. It's the simplest data type. They used to default to character, which was kind of a weird thing. If you have all missing data, it makes more sense to default to logical. Yeah. One of those slide update things. I try and keep my slides as up to date as possible, but small technical changes sneak through all the time. And I'm busier than usual this term, so I didn't double check everything. I did add a bunch of stuff to these slides though this afternoon. So there is some new stuff, like this Vroom stuff. That's new for this term. Okay, so anyway, that's for CSV files, TSV, stuff like that. Often you got to work with Excel files instead. If you're working with .xls, .xlsx files, stuff like that, I recommend using the read Excel package for reading them in. or the write Excel package for writing them. There's separate packages for reading and writing. It's kind of arcane reasons for that, but they're related. If you're working with Google Docs spreadsheets, you can use Google Sheets 4 and pull them directly down off of Google Sheets. I have a couple projects where they sort of just live pull Google Sheets data down all the time. It's nicer than manually downloading and then loading it. Just pull it right down off. You have to give it like the Google login that has access to it, but it can just pull stuff straight down. So the thing is, with read Excel, write Excel, all that, you don't keep any text formatting, color, comments, or merged cells. If you have Excel spreadsheets where the text formatting, the color, the comments, or the merged cells carry useful information, somebody made a mistake. That is a bad thing that people should not do. They do it all the time, but it's bad and it's dumb. Colors, text formatting, comments, merged cells are metadata that can only exist in that particular spreadsheet's format. You can't take like an Excel thing with merged cells and meaningfully convert it into a CSV. It doesn't make any sense anymore because the data would no longer be rectangular, right? It doesn't work, okay? These things get lost if you move out of Excel formats. This is a problem with proprietary formats. They only work in that particular piece of software. And if they change the software substantially, they don't even work between versions, which has happened with Excel. Okay, so if you have an Excel sheet that gives you a lot of grief, let's say it's got a bunch of merged cells, the simplest thing is usually to open it up and export the parts you need to a CSV and then import it into R and look at it carefully to see if everything worked. Though, if you got to do this programmatically, let's say you got a whole bunch of these, you need to do it regularly, you're in a business or something where they have these hideous sheets that people are manually doing input to, but you got to pull stuff off of them regularly. There are packages that can read the most abominable Excel sheets. If you need to get that stuff out, like meaningful formatting, merged cells, built-in pivot tables, if you have to extract the equations themselves from the sheets, use the packages Unpivoter or TidyXL. They can get all that crap out of those Excel files. They're harder to work with. They're very advanced. But if you need anything out of Excel, these things can dismantle an Excel sheet into its component parts, digest it into R, and grab anything you could possibly need. Okay, so these are this is kind of like these will eviscerate an Excel sheet. So they will break it down into all of its little XML parts, so you can do whatever you want to it. I don't know if they do writing out of complex tables though. Who knows? Yeah, TidyXL can extract data in comments. Yeah, so you can do everything. Actually, I think they both can get comments. Yeah, anything you want. What is a non-tabular Excel sheet? That's an Excel sheet that you open it up, and it has like completely uneven shapes to everything. So maybe a cell will span multiple columns, things like that. Usually it's still vaguely like rectangular, but it doesn't have even dimensions. One row might have 5 cells, the next row might have 2, that kind of thing. R doesn't know how to read that in as a data frame, and so the normal packages don't work. Yeah. Okay, you'll see those a lot though in business and government, so it's good to know how to deal with them. Okay, so next thing. Getting data out of R and into a tabular data format looks a lot like getting it into R. So if you want to write a CSV file, instead of writing read_CSV, you say write_CSV. You tell it the object that you want to turn into a CSV, and you give it a path. What this would do then, this would take that Billboard 2000 raw data I pulled in, and it would write it to a CSV file in my current working directory. So you can spit out a CSV file. If you're working with people using other software, CSV files make sense. In fact, my recommendation is, even if you're working with people who do everything in R, exchanging everything as CSV files is usually the safest thing you can do. CSV files are sort of the universal format, right? Everything can handle a CSV file. When possible, work in CSVs as your main storage format. Okay. So a thing about CSVs, of course, is that they drop any R metadata. If you save something as a CSV and then load it back into R, you'd lose things like this was character data versus numeric data, integer double. dates, all that kind of stuff. It loses all this metadata, much the same way that if you save an Excel sheet as a CSV, it doesn't know how the columns were formatted in Excel, right? You lose all that stuff. So if you want to save objects in R and preserve all that metadata, you want to save them in an R data format. And R has two native data formats. It has .rds. .rds is for storing a single R object as a chunk of data, okay? It doesn't save the name of the object, it just saves it somewhere on disk. You could save it, so you would use write_rds, the name of the object you want to save, and then you'd save it on your computer somewhere .rds. It will create a file on disk. If you want to load this back into R, you have to load it in and assign it to a new object. So read RDS would just print it to the console. If you want to capture that and put it somewhere, you got to assign it to an object. So you would say, read this RDS back in. There's the path on my drive. Assign it to some new object name. Okay. The other data type is R data. So while RDS can save a single R object, R data files can be an arbitrarily large number of objects. You could have 100 different R objects all in one R data file. You could store your entire data, like your entire global environment, in a single R data file. That's actually what R does. If you have it set to save your environment when you close R, it just writes one R data file that it loads when you start it back up. This is good for you saving multiple files, or if you want to save files and keep the object name. This is the reason I use them, is I like to keep the same object name for things I save when I load them back in. For this, you use the save function in R. You say save one or more objects, and then say, I want to save them to this file. You load them with load. Give it the path. Notice you don't use an assignment operator here because it automatically loads it in with the same object name it was saved as. Do whichever one of these makes sense to you and you prefer. It's purely a personal preference which way you do it. You'll see a lot of tutorials online where people use RDSs. You'll see a lot where they use R data files. I like R data, but it's personal preference. You do you. Okay. Either way, they're going to save all their metadata. Another reason to save things as .r files is they're pretty damn small, okay? So CSV files are basically an uncompressed data format. They take up a lot of space on disk. R files will tend to be like 1/10 the size or smaller of a CSV file, so they'll save a lot of room. They also load faster. If you really need something to load fast, though, don't use any of these formats and use a format like Feather or something like that, which is made for fast loading and saving. Okay. Another random thing, if you're asking for help from someone, me included, it can be useful to prepare a little snippet of your data. Dput will do this for you. If you have some object in R, like here I got the head of the car's data frame, its first 8 rows. If I dput this, it will print to console something that looks like this. It'll say structure, list, the variable, the first 8 observations of it, the next variable, there are 8 observations, some row names, and a class for it. You're like, well, what is this? If you copy and paste this into your R script and run it and assign it to an object, it will recreate the output of head cars 8. This is a way to email someone an R object in pure text. This is a kind of a handy thing for getting help from somebody like me. If you're working on like some dissertation data or something, you can't share the file, but you could share like 10 rows of it. Dput it, send it to me. I can copy and paste in the actual object with its original properties. Kind of a handy thing. Good to know. You may never need to use this, but just know it's there. Okay. So very often, probably, if you work as an RA, a postdoc, or something like that, you're going to be working with people who use Stata or SPSS. The postdoc I just got, the main PI on was mainly a Stata user, so I'm going to be spending a lot of time going back and forth with Stata shit. Okay. You can use a package to bring in or send out files to these other packages. Okay. So Haven is a tidyverse package for doing this. Haven can read Stata, SPSS, SAS. It can't do Minitab, I don't think, but it can do a lot of other common packages, okay? It's part of the tidyverse, so it sort of behaves like tidyverse stuff. The foreign package in R can do Stata, SPSS, Minitab, and some other ones. I don't know if it can do SAS. It probably can. I like Haven in general, but you can use either. For less common data formats, Google it. I've yet to encounter a data format that doesn't either have an R package to handle it or a clever hack, with one notable exception. I think I mentioned back in week 1, that was a bizarre database slice file. I did eventually find a hack to open it up then, so I guess even that one got invalidated. Okay. One thing I want to say about Haven that's really nice, if you load up a, say, Stata or SPSS data set in Haven, it keeps the variable labels. This is not a thing that will be done by the foreign package. Stata and SPSS have labels on their variables. R is not a language that likes putting labels on things. Haven will keep those labels so you don't lose that information. This is really nice. Question here in chat. Have you imported data from RedCap? Is there a format for that? There isn't directly a format, but there's a couple packages for doing it. So I have directed people to packages for directly interfacing with RedCap. I don't know what RedCap's native data output format is, but you can actually pull it directly from RedCap into R with API calls from a couple packages. I forget what they are, though. Can you give an example of labels? I don't have any Stata data lying around to give a good example. So labels are kind of an odd thing because in R, they don't have them. So I can't give a good example in R because by default, it doesn't have labels. In Stata, Stata files will have like a short variable. The reason Stata has labels also is because it used to, especially anyway, have very short maximum variable length names. Like it used to be like 8 or 9 characters. I think it's like 13 now, really small. And so if you want to know what var 25867 was, you needed some index. And so labels would be attached to that and would be a long sentence long explanation of what a variable is. SPSS does it too. So it's data labels on stuff, right? Yeah, it's like if you have a categorical variable and it's 0 to 3, but you want to know that they stand for, you can label them cats, dogs, pigs, and cows. That's for like a factor. This is for like whole variables. So if you have like var 31, you can have a label on it saying var 31 is gender, right? R doesn't usually use them, but they're built in with Haven and the labeled package in R. Okay. Another thing, if you encounter a mysterious file extension, the most common one is .dat. .dat is a meaningless suffix on a file. There's so many .dat files out there that it means nothing. The first thing you should do is using a good text editor that's like Atom or Sublime. Open it up and see what happens, or Emacs or Vim if you're that sort of person. Load them up. Very good chance it's actually a CSV file or a fixed format file, like, 80% of the time. If it opens up and it's got weird looking characters in it, it's probably a binary file and you're gonna have to track down how to open it up. Okay. So any questions about that before we move on to pivoting data? I'm gonna get into real code in a minute here instead of just gibbering about stuff. Okay, let us march onward. So I'm going to talk about tidyr, I should say tidyr, long R as Hadley Wickham says it, using tidyr for pivoting data. Okay, before we get to that, I want to give some basic advice on what you do when you load up a new data set. In other words, the kind of thing you might do when you load up the horrendous data set I'm giving you for your homework this week. First things to look at when you load a data. First, did the last rows and columns from the file make it in? So normally you'll notice real quickly if the first rows or columns of a data set don't make it in, but it's easy to miss that the last rows and last columns didn't make it in right. If this happens, you might have to do a different package for loading your data, or you might have to manually specify a range, or you might just have to dig into your Excel like file, whatever it's coming from, and see how they mucked it up and fix it, okay? So take a look at this. It's a common thing. If you see the beginning and the end of a file, both horizontally and vertically, looks fine. The middle of it's usually all right. Not always, but more often than not. Next, are the column names in good shape? Frequently, you'll load up some file and it will have atrocious column names for some reason. It could be because its original column names have spaces or weird characters in them, you name it. Or they begin with numbers and R doesn't like that. You might do something like modify a column names argument in your read CSV or something, or rename them afterward. Another thing I don't show here, which I'll probably introduce in the spring term, the last time I will ever teach this class, I will probably would say use the janitor package. Janitor is a package in R that has a clean names function. It will take the names for an entire data frame and reformat them into a uniform lowercase and underscore based system of naming. It's really nice to just kind of generate them and run it through so you don't manually rename everything. Okay. Another one, are there decorative blank rows or columns? This is a common thing. Sometimes you'll just get a blank like skip rows, or you'll get like a header row that has some descriptive information. You might have to filter these out or select them out, or you may actually have to read them in and say, ignore the first 5 rows of this CSV. And there's a skip command or a skip argument you give to read CSV, and it says skip the first n rows. Another one, this is quite possibly the most important of these. How are they missing values in your data represented? Are they loading in correctly as NAs? Are they coming in as blanks, periods, numeric values? So one of the most dangerous things is it's very common in survey data sets to represent missings with negative values or 99s or 999s. There is a quite famous story in the discipline of demography about a paper that was published, I forget what relatively good journal it is, showing a very unusual nonlinear relationship between marital satisfaction and frequency of intercourse. Basically, people who were having an enormous amount of sex were showing really low frequency or really, really high frequencies of intercourse, right? Very low satisfaction, very high rates of intercourse. So like, what is going on? The paper got published. They said it was some strange nonlinear effect. Those were people who had missing values for intercourse frequency, but it was coded as 9 or 99, I think. So it was basically people who were doing it 99 times, apparently were showing really low satisfaction. Well, they forgot to code their survey data missings correctly, and it drew their regression line way off, and they didn't do any basic descriptive checks. Make sure you know what your missings are coded as, otherwise you can have very embarrassing mistakes, okay? Especially in survey data, because sometimes they'll also have many, many different missings. Like I have a data set I work with that has, that does like 87 through 99 are different types of missings, because in survey research, there's a lot of types of missings. There's different types of skips, didn't ask, skipped in a certain wave, you name it. Lots of missings, look for them, okay? So once you've identified these, use mutate or if else to fix these. You could do all sorts of other things to sort of get through them, but you probably have to manually handle them, okay? Read CSV, I think, also takes an argument of missing values, and you can give it a vector, and everything you give in that vector will just be turned into an NA. So you can also do that like that, okay? Lastly, are there character data, like zip codes with leading zeros, being loaded in as numeric data? So if you have something that looks like numeric data, but like leading zeros matter, it's not numeric data, it's character data. So zip codes are character data because there are zip codes that begin with 0 in the Northeast, okay? You don't want them loaded in as numeric because those zeros will get dropped. Best way to do that is to modify your column types argument and specify its character data, or you could use mutate, flip them to numeric or character. If they cut zeros off, you can add those zeros back in with tools we'll learn in a couple weeks. Okay, so wouldn't you want zip codes to be a factor? Maybe, but not necessarily. So I tend to think of factors as something of a relatively small number of levels. If I'm working with every zip code in the United States, I may eventually want it to be a factor, but I probably don't want it to load in as one. I may also want to paste it together with other things such as the subzips, you know, the little 4-digit tack-ons. Maybe, maybe not. It's basically a factor, but I tend to make all my categorical data character and worry about making it a factor later, only when I specifically need a factor, because factors suck. And we'll talk about why factors suck a little bit later in this lecture. Okay, so here's an example of slightly messy data that to a normal human is not messy at all. So here's some enrollment data from this class, from like the first time I taught it. So there is a program, and I keep, I think I have these incorrect. Do I have these put as gender? Good, I do. Okay. So I have a program, and then I have, this really should be like men, women, gender rather than sex, but you know the jam. Anyway, I have a program, female and male. This is Evans School, so the Evans School of Public Policy. 10 female, 6 male students, arts and sciences, 5, 6, public health, 2 and 3, other, 5 and 1, that kind of thing, right? Okay, this is a nice readable table for a person. This is not that readable for R. So if you look at this, when you look at this, what is an observation of data here? An observation of data is a group of students from a program of a given gender. So a single observation is like 10. There are 10 female Evans School students. Well, what are the variables here? The variables are the program and then gender. Gender is in 2 different columns, but it's 1 variable, okay? This is why it's messy data, right? So the issue here is gender is a single variable, but it's in the column headings instead of its own column. The count is a single variable, but it's been spread over 2 columns. So it would be better to have program, gender, count of students, which would result in me having twice as many rows, okay? Because you'd have Evans School, female, 10, Evans School, male, 6, okay? That would be readable data from an R standpoint. So this is messy data. It's very readable, but it's not what R expects. The tidy version looks like this. Each variable is in a column. There's now a program, a gender, and a count. Each observation is a row. So one observation is 10 female Evans School students, 6 male Evans School students, and so on. Okay, this is now ready to throw into ggplot. If I wanted to, I could put like, I could say X equals program, group on gender, Y equals count, and make a column plot out of this. This is ready to go into ggplot. Here, like this, I can't. I would have to plot these as 2 completely different things. They're different variables. I want them all in one. Okay. So the Billboard data we loaded earlier is ugly. It is a hideous thing. So these are the data we're going to work with. It looks something like this. We have like the year of the song. They're all 2000 because it's the Billboard Hot 100 of the year 2000. We have artist. We have what particular track. We have the time of the track, in this case, 4 minutes, 22 seconds. Then we have a terrible data format. It's organized by the date it entered the Hot 100. So in this case, it entered on February 26, the year 2000. And then there are 76 columns, and those are the rank the song was in that week. So week 1, it was rank 87. Week 2, it was rank 82, then 72, 77, 87. This is an abomination, right? So we have one measure, which is the rank of a song spread over 76 columns, okay? If you want to plot this in ggplot, it ain't gonna like it, okay? What we want to do is reel this back in so we have 1 column for the numeric week, so week 1 through 76, and 1 column for the rank that song was in that one, which is going to end up with a lot of repetition for these values over here. Let's say that Baby Don't Cry was on the chart for 25 weeks. It would now have 25 rows. That's the kind of data we want. Okay. So the Billboard data, like I said, what is an observation in this data? It's a week since entering the Billboard Hot 100 per song. So in an ideal world, we would have 1 row per week per song, right? Okay, what are the variables? Most of them are obvious. The year, the artist, the track, the length, the date it entered the Hot 100. But then their variables are the week since it entered the Hot 100, which is spread over many columns as the names of the columns, and the rank during that week, which is in the cells of those columns, okay? Those are 2 variables spread across 76 columns, okay? The values in the data are things like the year 2000, 3 Doors Down, Kryptonite was a 3 minute and 53 second song that hit the chart on April 8th, 2000. But in week 3, when it was rank 68, we'd have to go track it down in the week 3 column and then find rank 68 when they should just be in their own columns. Okay. So To define tidy data, which I've now shown you an example of, I'll answer that one in just a second. Tidy data are data where the values for a single observation are all in their own row. The values for a single variable are all in their own column, and there's only one value per cell in the entire table. Again, this is a simple tidy data definition. This is actually based on standards for relational databases and data storage. If you really want to learn about proper data storage, learn fundamentals of relational databases, because that's where the stuff is derived from. Okay, so in chat, if this were in a database, would you want a one-to-many relationship between song and weeks on Billboard? Yeah, because you have the song, essentially, you would have a table that would be the song information, and another table that is essentially like that's the weeks for that song. You can think of it as one table per song. It really depends how you want to store it up, but it really is a one-to-many. So song weeks are those observations, but there's also song-specific data that would be repeated otherwise. Yeah. Yeah. Okay, so why do we want tidy data? One big one is just sort of intuitive. It's easier to understand many, many rows than many, many columns. It's easier for most humans to scroll up and down than left and right, just in our normal way of interacting with information. We tend to like taller things rather than wider things. I think it's a linguistic reason, but so be it. Next is a pragmatic one. It's required for plotting in ggplot2. It expects long, tidy data. If you want to plot with it, it's really hard to use really wide data. Another thing, it's also expected for almost every type of statistical model. Most statistical procedures, hierarchical models, mixed effects models, standard regression models, just about everything out there expects long data. The only exception to this is structural equation models, which expect wide data. Everything else is long data. Another thing, there's fewer confusing variable names. More rows means fewer columns, which means fewer variable names, which means fewer redundant variables. Long data tends to be more compact like that. It's easier to think about. A big one also is that there are fewer issues with missing values and imbalanced repeated measures. The idea is if you have only one column for each variable in the data set, where missing values appear in that column, you just delete the row. You don't need the row if the only value that would be represented there is a missing value. This means your data tend to take up much less space on disk if they are in long format than wide, and that scales with missing data. The more missing data there are, the smaller and smaller long data files get. We're going to see an example of this with Billboard in a minute when we massively shrink this data set by deleting all of the blank cell values where songs were not on the Billboard in that week. Nothing was on the Billboard in week 76. That column shouldn't even exist. Going to long data deletes all that. Okay. So the tidyr package is a package that gives you lots of functions for tidying up data, most particularly things for reshaping data from wide to long, like reshape in Stata or vars to cases in SPSS. Its key functions are pivot longer. This takes a set of columns and pivots them down to make 2 columns and many more rows. Okay, you can provide names for them. Basically, you'll give it a name column that stores the old column names. So like all the weeks, before we had 76 weeks, week 1 through 76 would go from the names of those columns to being values in a new names column. And then the value column would store all the values that were underneath those column names. So all the cell values. So no matter how many columns we pivot down, you're going to get 2. One that contains the old column names and one that contains the old column values. Okay. The opposite of this is pivot wider. This will invert it by taking 2 columns, a name and value column, and pivoting them up into multiple columns. For this, you'll get 1 column for each unique value in the name column, and then all the value column ones will be allocated appropriately to the columns. There's also the separate function, which will pull 1 column apart into multiple columns. This is a common thing you do after pivot longer if you need to pull out like numeric values out of those column names. Extract numeric, I'll show you, does a simple version of this where, for instance, if we pivot week 1 through 76 down, we don't want to say WK1, we just want the number 1, the numeric value of that week. We can yank it out with extract numeric. There's also a function I'm not covering today called extract. This is for pivoting a column into multiple sets of columns. it's pretty advanced. You can actually do some of this functionality in pivot longer also, but it's beyond sort of what I want to get into in the class. It's really complicated. Okay, so let's use pivot longer to get those week and rank variables out of their current 76 column layout to get us way fewer columns and way more rows. So here I load up tidyr and dplyr, and I say, we're going to create a new object called Billboard 2000. I'm going to assign to that Billboard 2000 raw, and then pivot longer. I'm going to pivot every column that starts with WK. There's 76 of them, WK1 through WK76. This is that same syntax you see in select. You can use it to select any columns you want, so you don't have to write all of them out, okay? Then we're going to say, I want the names, that is the old column names, are going to be stored in a new column called week. The values under those columns are going to be stored in a column called rank. So there's a question in chat. Why do we need dplyr here? I need it for the pipe. And I'm going to use some dplyr functions in a minute, but right now I'm using it for the pipe. So I pivot my Billboard 2000 raw data. I get its dimensions. Now it has 24,092 rows and a mere 7 columns. I have massively shrunk these data horizontally and increased their length vertically. Okay, so you can use these selectors, like I said, starts with week. I could have also said WK1 colon WK76 and would get all the contiguous columns. I could use all sorts of other things. I could name all the columns manually, okay? Any of that stuff you use in the select function can be used here. Okay. I also think I would have had used starts with here from dplyr also to make this work, so dplyr needed for that too. Okay, so this is what the data look like now. If I get head on Billboard 2000, I can actually display them all horizontally, right? There used to be 80 something columns, now there's 7. You'll see I have 2000 Tupac Baby Don't Cry, which is a 4-minute 22 song from February 2000, is now repeated many times. Then we see in week 1, its rank was 87, in week 2, it was 82, and so on. These data, all of those wide columns have been converted down. This is long data because I have many repeated observations for the same song. But this song has now 76 rows. There's 1 row for each week with its corresponding rank. So this is nice long data. Right away now, this is actually kind of usable in ggplot. If I converted this over here to numeric values, I could literally plot all this stuff right away. It's great, but it's not perfect. If I say summary Billboard 2000 rank, okay? If I look at this rank value, it starts at 1, it goes to 100. That's what it should. It's the Billboard Hot 100. The best rank is 1. The worst rank is 100. But there's something very stupid here. Our data set is 24,000 rows long, and 18,785 of them have an NA for rank. So what this was is that all of those 76 columns we had for ranks, the vast majority of them, the song wasn't even on the Billboard at that time. So we pivoted them down and we got 18,785 missing values. This is stupid. It's wasted space. In our new long data format, if we look back here, you'll see if there's an NA for rank, the whole observation is useless. We don't need to know week 5 it wasn't on the Billboard. We could know that by deleting the row. So we're going to do that. The idea, we don't need all those NAs. They don't convey any useful information. A missing value here, there shouldn't be an observation. So what we're going to do is we're going to pivot a little bit better. I can add to my original pivot longer statement. So remember, Billboard 2000 raw and then pivot longer starts with week. The names go to week, the values go to rank. I add values drop NA equals true. This says after pivoting, if the value column rank contains a missing value, delete the row. It's useless to us, and it is. If I just go ahead and say drop any NAs for rank, I then get summary on rank. I get the exact same other values, but now there's no NAs there. It deleted them all. So this just went ahead and deleted all those values that are useless. If I get dimensions on Billboard 2000, now it's only 5,307 rows and 7 columns. So this shows you right away that the vast majority of cells in this original table were useless, wasted space. Of those 76 columns, most of them contained nothing of use to us. Okay, So this gets rid of those missings. Way fewer rows. That makes sense so far? Questions? Okay. Okay. So as we see back here, this week column right here contains numeric information, but it's character. It's WK1. The WK doesn't convey any useful information. I would like to make this week column to be numeric weeks. Okay, so it's character, but it should be numeric. If I get summary on week here, it says it's a length 5,307 character vector. Useless to us. I want it to be numeric. tidyr has a convenience function that will take a character column and delete all the character values in it and keep only the numeric values. If I say, take the Billboard 2000 data, mutate my week column, so I'm going to overwrite the week column, parse number week, all this is going to do is going to go through, and anywhere it finds a alpha character that is A, B, C through Z, right? It's going to delete them. It's going to leave behind only the numbers. If I now do summary on week, week now begins at week 1 and ends at week 65. You know what this indicates to us? Because we only deleted our missings on that previous step, not a single song spent more than 65 weeks on the chart. So the last 12 columns or 11 columns of that data set were completely useless. Weeks 66 through 76 were useless. Nothing was on the chart that long. Okay, so this parses the number, converts it to numeric. We now have a numeric week variable, which we can use for plotting or something like that. Okay, if you need to do something more sophisticated, like let's say your week value had like a mix of numbers and letters, and you only wanted some of the numbers, you could use pattern matching that we're going to get into in week 8, I think. Yeah, week 8. Okay, with regular expressions. Okay, another thing we could do is instead of parsing the number, we could also make pivot longer do this for us. As you can see, pivot longer is a really powerful function. I say here, take my Billboard 2000 raw data, do all the same pivoting things as before, but then I add some more stuff. I say names prefix equals WK. This means all those week columns, I'm saying they began with WK. I want you to delete that. And then the names column should be transformed into an integer column. This just says transform that names column. The column is going to be week as integer. The resulting data, if I get the first 3 observations we see, week has been converted to a numeric integer column. So it did the parse number thing for us. Okay. So pivot longer can do all sorts of powerful things in one function statement. You don't have to. You could have done the dropping of the NAs with filter. You could do this with parse number. You do you, but just know you can do it all in one call if you want to. It's a powerful function. Okay. So what we got now is a week and rank column. Let's mess with the other columns. So the track length column we have in here is things like, I'll show you again, 4:22 character data. Okay. Well, minutes colon seconds is very readable for you and me. I know that that is 4 minutes and 22 seconds, but it doesn't mean anything to a computer. If we want to do a plot over length of songs or something like that, the computer doesn't know how to read 4:22 into something useful. Let's make it into something analytically friendly. So what I'm going to do is say, I want to take the Billboard 2000 data and then separate the time column. I'm going to separate the time column into 2 new columns. They're going to be called minutes and seconds. I'm going to separate them based on the location of a colon. So what this says is if you encounter the number 4:22, it's going to delete the colon, put the 4 in minutes and the 22 in the seconds. So this is where the first thing goes, the second thing goes, and the thing that separates the first thing into the second thing. And then I want to convert it equals true. This says convert it into the simplest data type that can store that information. In this case, it's going to be the number 4 here, the number 22 here, which can be converted to numeric data. So this whole statement says we're going to separate things by colons and make 2 numeric columns. But you know what? I don't actually care about the minutes or the seconds. I want to make a single track length column. So I say, we're going to mutate a new length column, which is equal to the number of minutes plus the seconds divided by 60. This gives us a decimal place minutes length. So if a song is 3.9 minutes long, that's what it is. We don't know how many seconds exactly, but it's pretty close to 4 minutes. This is a decimal length. Then I say, let's delete the minutes and seconds columns I created up here because I'm only interested in length. If I get summary in my new column, we can see the shortest song on the Billboard Hot 100 of the year 2000 was 2.6 minutes long. The longest one was Freebirding out here at 7.833 minutes, right? Super long song. Okay, so this is something that might be useful to you. You can split something that contains pseudonumeric information by some character value. So again, somebody asking here, sorry, what is the goal of convert equals true? If I did convert equals false, the resulting minutes and seconds columns would be character data instead of numeric data because the original column time was character data. Convert equals true converts them to numeric, which is nice. So I can do some math with it on the next one. Now we got some track lengths. Okay. So another thing I want to show, not using the Billboard data, is pivot wider. Pivot wider is the opposite or the inverse of pivot longer. This is something you use if you have data where the same observation takes up multiple rows and you want to undo that. Here's an example. Here's data where I have a group, a statistic, and a value for that statistic. So the thing about this is actually bad data. This value column here does not store the same type of information in each one of these cells. This is different types of variables in here. The number 1.28 is not the same metric as 1.0 because this is a mean, this is a median, this is a standard deviation. I probably don't want these all in one column. One exception would be if I was going to do some sort of interesting faceted or grouped plot or ggplot, you might want it this way, but this is really not the kind of data format you probably want for these sorts of data. So a common cue for using pivot wider is when you've got measurements of a different quantity all in the same column. That's what we have here. This really quickly is just a slide where I'm generating these data to do it. It's not important. What is important is I can take those data and say, I have my too long data. I'm going to pivot wider where my names are from statistic, my values are from value. If I look back here, you'll see there's a statistic column and a value column. What it's going to do is it's going to look in statistic, and for every unique value of statistic, it's going to create one new column. So we're going to get a mean column, a median column, an ST column. Mean is going to have the value for 1.28 and 2.81. It's going to reduce this down to one row per group. Okay, so now we have group A, mean 1.28, median 1, ST 0.72. Now it's proper tidy data. Okay, I don't use pivot wider too long, but it's good to know it's there if you need to invert like some sort of pivot longer operation. Actually, I do commonly use it, but I usually commonly use it when I pivot things super long, like I'll pivot every variable in a data set into one column and then pivot it back out into the format I want. That's a common thing I do. You know, if I've got like 70,000 columns and I want it to be about 100 columns, I might pivot them all down into like 2 or 3 columns and then pivot out a subset of them one at a time. That's complex. Don't worry about if that's mind bending. That's a thing you'll do. Okay. So let's answer some actual questions with these data. So what I want to do is I want to look at the songs that hit #1 at some point on their time on the Billboard Hot 100, and I want to see the trajectory they took visually to get to #1. So what I'm going to say is, let's take the Billboard 2000 data and then group it by artist and track. The idea here is I want to get the best rank these songs got, song by song. I'm grouping by both artist and track in case 2 different artists had a song of the same name. I don't think this is the case here, but it's a good way to be safe. So I group it by artist and track, and then I mutate a new variable. We're going to create a variable called weeks at #1, which is equal to the sum of rank equals 1. So what this does here is this goes down within every artist and track. It's going to look at every observation and test to see if rank equals 1. It will return a true if it was rank 1. That is the best rank you can get. False otherwise. But by summing up the trues and the falses, the trues become ones, the falses become zeros. So this ends up being a numeric variable that counts the number of weeks a song was at number 1. Okay, this works because I've grouped within artist and track. I'm then going to calculate the peak rank, the best rank this song ever was. I'm going to say, if else, any of its ranks are equal to number 1, it hit number 1. If none of these ranks are number 1, it didn't hit number 1. All I care about is whether it was rank 1 or not. This here, any rank equals 1. If any ranks for that song, for that artist were 1, this whole statement returns a true. If all of them are false, it returns a false. Okay, so I then ungroup my data. If you do a group by and you don't do a summarize, you just do a mutate, your grouping doesn't go away at the end. And so just in case, it's often good to manually ungroup your data afterwards in case you want to do something with it later. So I just sort of reflexively ungroup it. Okay, do I peek the data? No, okay. So we now have 2 new columns, the number of weeks it was at number 1 and the best rank it ever hit. Let's do something with it. I load up ggplot here. I say, we're going to create a plot called Billboard Trajectories. This is going to be the ggplot of the Billboard 2000 data. The x-axis is week, so we're going to be looking at time on the x-axis. Y is rank, so we're going to be looking at the rank it was vertically. I'm going to group on tracks because we're going to do a line plot of the track ranks over time. I'm going to color it by peak rank. Peak rank is the best rank it ever hit. I then say, I want to do a line plot where the size is equal to peak rank. So we're going to have a bigger size for songs that hit number 1. Alpha 0.4 makes lines partially transparent because there's going to be a lot of lines on here overlapping. I logarithmically scale my x-axis for a reason we're going to see in a minute. There's way more observations early on in the low weeks and in the late weeks. Logarithmic scales squish stuff in the later weeks and expand the stuff on the earlier weeks. I'm doing this because I want to see more of those early weeks. I reverse the y-axis. The best rank a song can get is rank 1. So I want rank 1 on top instead of on the bottom. Scale y reverse flips your y-axis. Then I just kind of tweak it up to make it look the way I want with a manual legend and stuff. This is what we end up with. This is the trajectory of every song on the Billboard Hot 100 in the year 2000. The red lines are songs that ever hit rank 1. So you can see, by and large, they actually follow a fairly similar trajectory. They enter pretty strong over here. They arc up and hover around in like week 10-ish usually. They stay on as number 1 and they fall off kind of quickly after that. There's another thing we see on this plot that shows the importance of plotting your data, something we probably would not have noticed if we looked at our data in tabular format. There's a lot of data censoring over here. You'll notice if a song doesn't rank really high on the Billboard Hot 100, they just deleted it from the data after week 20. Why did they do this? I do not know. But this would be a problem if we were using these data for actual analysis. They censor things that didn't go very high on the ranking. Just a thing they do. I don't know why. But plot your data. One of the most important things about data analysis when you're working with it, you got to plot your data, otherwise you don't know what's going on very often. This would be a very difficult pattern to notice without plotting, and it's very obvious plotting. Okay, so these are the trajectories they took within weeks. This isn't, however, calendar time. Maybe we want to work with calendar time. Okay, so another question. Which songs were number 1 the most weeks? I could say Billboard 2000. Give me the distinct observations of artist track and the number of weeks they were at number 1. Arrange them by descending weeks at number 1 and look at the top 7. We can see that, like Destiny's Child here, 11 weeks at number 1. That's a long time for a year. And then we get all the way down to my man Enrique at the bottom, which is why I do head 7 to keep him on the chart. 3 weeks at number 1. Okay, this is important information. If you existed in this time, people are getting younger every year that I teach this. Billboard Hot 100 year 2000. These are my times. Okay, so important information. Okay, the next section. I'm going to talk about dates and times, which unfortunately we're going to move through pretty quickly because I apparently rambled too much this one. It's 4:54. I'm going to talk about dates and times mainly using the LubriDate package. Okay, so one thing we have the date the song's first charted, but we don't have dates for the later weeks. We could now calculate those later weeks as dates because the data are now tidy and we can do some simple math with them. So what I'm going to say here is I'm going to take my Billboard 2000 data and then mutate a date column, which is equal to the date the song entered the Billboard Hot 100 plus week minus 1 times 7. What shenanigans is Chuck doing here? Well, the date.entered column is already date data. Date data is numeric and its units are days. If I add 1 to a date, it increments at 1 day. So here I say date.entered, and then for every week it was on the Billboard, I add 7 days to it. So this gives us a calendar date for the given rankings. If I take a peek at these data, we can see this Tupac song entered the chart on February 26th. So for week 1, the date is February 26th and its rank is 87. But for the next week, it was March 4th. A week later, March 11th, March 18th. So using a little bit of numeric shenanigans, we can get rolling week dates that we could plot, say, in ggplot. So if you know this about dates, it becomes kind of handy. Just add numbers to them. You can increment them by days. And because it's a date object, it knows how to handle the fact that February, for instance, has 28 days. You don't have to do some math figuring out the correct number of days in a month. It handles it for you. Okay, that's why date and time objects are nice. They know how to work a calendar. Okay, so I can plot more or less the same plot over calendar time. I'm going to skip over because the code's not that important. What we get now is a calendar time plot of all the songs going up and down. This is a ball of hair. The reason this plot is a ball of hair is because every single rank from 1 to 100 is represented at every single week in the chart. So no matter what, every line is here and they never overlap at a given point. But because that's true, you just end up with a mess of these things crossing over each other. What's cool and useful about this plot is it shows you the Billboard Hot 100 of the year 2000 is not limited to weeks in the year 2000. This line right here is January 1st, 2000. This line right here is December 30th here, 2000. You'll see that songs go over the year 2000, and some of them are in 1999 over here too. This is another data quality thing. Basically, a song could chart on, if a song charted at any point on the Billboard Hot 100 for the year 2000, they kept every week it was ever on the Billboard. This is something you might not have noticed quickly and easily without plotting it, but it becomes really obvious when you plot on calendar time. This plot also reveals a powerful thing about ggplot. You'll notice here that it says June, July, August, September, October like this, even though I had date data. If you want to make nice labels, you can use scale x date and then say, for instance, I want my breaks to occur every month and I want them labeled %B is 3-letter month abbreviations. So instead of having specific dates, it just says June, July, August, September, October. Date objects are also nice because you can use them for really nice ggplot labels. Steal that code if you're interested in it. Okay. So to practice working with a little finer grain date time data, I'm going to use some Seattle Police response data. So this is 911 incident response data from the Seattle Police Department. This is data from a single day of police calls, but it has date time information, which is nice. I think it's a single day. I'm not positive. Okay, so I just load in SPD raw as this CSV file that you can pull down off my website. It loads in with a bunch of things. You could do some interesting stuff because it has like longitude and latitude if you want to map it. But for right now, I'm just going to work with the, where is it? There are dates and times. Event clearance dates. And I I think that it contains a time here. Oh, at scene time, stuff like that. Okay, we're going to play with this stuff. So if I quickly glimpse at these data, you'll look over here and see what we care about is, okay, yeah, there's things like, okay, the first incident here was a car prowl theft, type car prowl, whatever, but event clearance date is March 25th, 2016, 11:58 p.m. and 30 seconds, right? This is date time data. We want to turn it into a date time object and then do useful things with it, okay? So let's do that. So to do this, I mostly would work with the Lubridate package. The Lubridate package makes it much easier to work with dates in R as compared to base R functions for it. So I don't even show any of the base R ways to deal with dates and times. Just use Lubridate, makes your life much easier. So if I look at the SPD raw event clearance date column, it looks like this. This is raw character data. So it just is like 03/25/2016 space 11:58:30 space PM. Okay. So if I wanted to digest all of this into a nice date time object, you have a couple options. One option would be to manually slice it up and be like, well, it's day 3 or day 25, month 3, year 2016, make columns for these things and stuff like that. Okay. Don't do that. Never do that. Let Lubridate do all the hard stuff for you. Instead, what we're going to do is we're going to load up the Lubridate library. And now I'm going to say, take this SPD raw data and then mutate my event clearance date. So we're just going to overwrite it with a modified version and use this glorious function, MDY_HMS event clearance date. Say the time zone is the West Coast time zone. And that's it. It then prints out and we see it's now a data type of POSIX CT, which I'm going to talk about in a second. And the data now shows format 2016-03-25, 23:58:30, 24-hour time, ISO standard dates. So what is this? This is the glory of Lubridate. This is a function called month, day, year, hour, minute, second. Lubridate has a different function for every possible combination of these things. You just use that function that maps to the way the data look. This is month, day, year, hour, minute, second data. Lubridate takes care of the rest. It figures out if there's an AM and PM over here. It figures out if there's slashes or dashes between it, if there's a space here, if these are colons. It figures all that out for you so you don't have to mess with it manually. It reads it, digests it, and spits out a date time object so you don't have to do anything complicated. This is a massive lifesaver. Before Lubridate existed, it sucked to work with dates and times, and now it's just, boom, it just works. Okay. So if this was instead something like it said 2016/3/25, you would use YMD instead. Okay. Does it work when the months are spelled out like January? Yes, it's very smart. It can read most common abbreviations and things like that too. Sometimes you'll have to manually specify stuff, but Lubridate's real smart. They use some sort of interesting behind the scenes package, some sort of library for digesting these things into usable stuff. Anyway, quick aside on time objects. Time data are weird, okay? So R uses two primary formats for storing data, which are international standards. Everything really uses these data standards, but they're important to know about. There's POSIX CT. This is a numeric vector of seconds since the beginning of 1970. When you store a date time object in R, it's a number. It's a number of seconds since January 1st, 1970. This is the universal standard for time in computers. It's the Unix standard for time. If you have a time date that occurs before January 1st, 1970, it will be negative. Doesn't matter how far back. It could be a BC one. It's a very large negative number. Okay. POSIX LT is a named list of vectors containing lots of date time information. Most of the time, it's POSIX CT. Can R work with century day codes? Probably. I've never done it myself. If you send me an email, I can look into it. So here's a question from Izzy. Does it matter whether the separator is? No, it doesn't at all. LubriDate figures out the separator. Okay, we usually work with POSIX CT. LubriDate gives us functions for dealing with all these things, so we don't have to manually work with them. Okay. It's often really much easier to convert time to standard numeric values and do modifications to them and then convert them back, or don't convert them back at all, particularly if they're like a variable in a statistical model. In a statistical model, POSIX time doesn't make sense. Make it some sort of numeric value and use it. Okay. So some useful functions with date time objects. If you have something like SPD event clearance date, which remember is a date time object, if I say as.date for this thing, it will basically cut off the hours, minutes, and seconds and return just the month, or sorry, just the year, the month, and the day. As.date spits out a date. You can also do things like take this date time object, tell me what weekdays it is. If I do weekdays on it, it says, well, this day was a Friday. It knows how to convert calendar time into the days of the week. I can also do math with them. Here's a date time object plus duration hours 1. This says add 1 hour to this time. Now the original times were, I think they were 2016, March 25th, 11:58 p.m. You'll see by adding 1 hour to it, it's rolled over to the next day, the 26th of March, midnight, 58 minutes. So by adding 1 hour to it, it rolls it over appropriately for clock time. This is why it's nice to work with dates and time objects. They know how to do things like roll them over after 24 hours. Okay, good things to know about. So here might be a question. What time of day were different incidents cleared in these data? I might say, take my SPD data, select the initial type group in the event clearance state. Initial type group is the type of crime. I'm going to mutate hour as just the hour of the given date time object. This pulls out a numeric hour. Then I do a quick plot where X is hour. I do a histogram. Histograms only take an X aesthetic and they bin it up and the height is its Y. Facet wrap on the initial type group, and we can see something like this. So the x-axis here is hours 0 through 23, 23 being 11 p.m., 0 being midnight after, right? And so we can see, these are different times of days. There's different types of incidents that are more common. Liquor violations tend to happen right near the end of the day, 9, 10 p.m. Suspicious circumstances are more common in the evening, sort of thing. Traffic-related calls spike also when liquor violations spike. Makes sense. Thefts tend to happen in the evening, that sort of thing, right? This is sort of time of day information. Okay, so this is using some time date information for something useful. Okay, so let's work with this using factors. So something we'll note in here, the most common calls here are suspicious circumstances, traffic calls, and thefts, but they're arbitrarily just sorted alphabetically. Maybe instead with this plot, what we would want is the most common things, suspicious circumstances and thefts, to be listed first and the less common things listed afterwards. The only way to do that in ggplot is to mess with factor levels. So let's go ahead and do that real quick before we run out of time. Okay, so factors are a very common data type in R, but they're fussy and they're annoying. You need to know at least a little bit about factors to maximize your use of ggplot and also like maximize your ability to manipulate statistical models later. So one important thing about factors is the order of your factor levels controls the categories or the order of categories in tables, axes, legends, and facets in ggplot. If you want to reorder the way things categorical data appears in a ggplot, you got to change the levels of the factor. Often we want to plot interpretable and aesthetic pleasing order of categorical variables or from high to low values. We don't just want to have Alabama first every time we work with states, right? Okay, we have like life expectancy. We really don't want to show Alabama first. It'll scare people off. Okay, so the lowest level of a factor variable gets treated as the reference level for regression models. So sometimes you want to change this reference level. To do that, you got to modify the factor levels. Reference levels are by default alphabetical. We don't always want that. Okay, So the Typeverse family of packages has a package for working with factors. It's called 4cats, that is 4 categoricals, okay? Its logo is a great picture of cats. This package replaces most of the base R factor functions with ones that are a little bit easier to use. It has a nice manual if you're interested. I'm going to show a couple examples. So 4cats already is on your computer if you installed Tidyverse as a whole. You can load it manually directly using library 4cats. Let's say I want to look at something like the initial type group. I'm just going to glance at SPD times initial type group, and we can see it's a character variable with values like theft, trespass, crisis call, okay? I could take this initial type group and convert it to a factor using factor. I look at it again, and now it says it's a factor with 30 levels. The first level is animal complaints. Animal complaints alphabetically comes first, so that's what's going to be the first level. If I now say I look at SPD times initial type group, I convert it to numeric, I look at it, you'll see the first observation, theft, is actually the 25th level of this factor. This isn't meaningful that way, but just know factors have this underlying numeric representation, and their levels don't come in a meaningful order other than alphabetical. This just indicates to us that theft up here happens to be alphabetically the 25th level of this. So if you sorted all the different levels in here alphabetically, it'd be the 25th one you come across. Is this a meaningful way to sort our data? Not really. Let's fix it. Okay. So if you want to re-level by frequency, that is, re-level your factors so that the most common value comes first, 4cats has a handy function to do this for you. I can say, I want to take the SPD times data and then mutate my initial type group variable. I'm just going to modify that same variable is equal to FCT underscore in frequency of initial type group. What does this do? This automatically figures out which of these initial type group levels are the most common. It orders them all by the frequency that they appear and alters their levels. So the most common one comes first, the second most common one comes second, and so on. And the last level will be the least common level in the data. So if you've got 500 rows of data and you have 499 of them for one factor, that one should probably come first. This does that for you. Now, if I look at the levels of SPD initial type group, you'll see the first level is now suspicious circumstances, which was the most common police call. The second most common was traffic related, then theft, then disturbances. It's reordered the levels to, instead of be alphabetical, they are now the order of frequency they appear. This is the exact same plot I just ran on that other slide, but by reordering this factor level initial type group, now the plot is ordered by the frequency of the calls. So the first level is suspicious circumstances, then traffic related, theft, disturbances, parking violations, and then all the way down the least common, there was a single call for person down or injury. This is a more meaningful and useful way to plot all of your data, right? Put the most common stuff first is what people care about. You're absolutely right too. You see last call. So you've got 2 a.m. bumps on some of these. Yeah, should be popping up stuff right there with traffic related calls. Well, it's not too much. They're probably right around, should be right around there. Suspicious circumstances. Yeah, hard to see. Anyway, yeah. So do this with your data. It's usually more useful to reorder your factors. Don't just make everything alphabetical. Okay. Other ways to reorder, though, you're not limited to reordering by, say, the frequency of a variable. You can manually reorder based on any kind of function you want, and you can reorder also by other variables. A general function for doing this is FCT reorder. The way it works is you give it a factor you want to reorder, some quantity you want to order it by, and some function to apply to that quantity by levels of the factor, and it'll reorder it. I'll show you an example. So this is something that's really useful, say, if you want to make the legends on your plot go from highest to lowest values. You could use like maximum or mean or something like that. I'll show an example here in a second. Another thing you might want to use is FCT relevel. FCT relevel, you give it a factor and then you give it a level. And all this does is it leaves all the levels in their original order, but puts the one you put in reference as the first level. This is a quick way to rotate some categories at different reference level before it goes in a statistical model. It's good to know how to do. Okay, let's show you an example of reordering. I'm going to plot quickly. I say Billboard 2000 data, filter to only JZ, mutate so track is a factor, and just mutate to factor to show you what this is going to do. I'm going to make a quick plot with a bad legend. This is just the week the song was on the Billboard, its rank. I'm going to group on tracks. I can make a line plot, color it by different tracks. I get a plot that looks like this. These are different JZ tracks, but notice something about this. This legend doesn't line up with the way that the data are plotted. So the first track listed is alphabetically anything, but if you look here on the lines, it's actually the one in the middle. Big Pimpin' right here is the second one, so it does line up with this one, but then Do It Again here is here like this, when it should be, something else. This is not a legend that's lined up with our data. It would be better, say, if this legend lined up with all of our lines. An even better option would be not to use a legend. It would be to actually draw labels on the lines, but not going to do that today. Okay, so what I want to do is reorder this legend. So what I'm going to do here is say, let's take the JZ data and then mutate track. So I'm going to overwrite the track variable by factor, reorder the track variable. Let's reorder it by the rank column, its minimum value. So this says, go find the minimum value for each specific track on here, its minimum value of rank. In other words, it's going to get reordered, the factor, by the best that song ever did. If a song hit number 1, that's the minimum it can get, and the best, it would be the first level here, okay? I do the exact same plot otherwise, and what it's done now is you'll see, I Just Wanna Love You is at top on the plot because it had the highest overall rank, and it's the first one on the legend. Big Pimpin' is the next overall, it's the next one, and so on and so forth. So this is a way to quickly modify your factor levels so they correspond to something meaningful in the data and the way it's going to get plotted. Little tweaks like this can make your plots a lot better. This is a faster and easier to read legend because the top one here is the top one on the plot. The bottom one here is the bottom one on the plot. Okay, do that kind of thing when you make plots. Little tweaks make things a little bit more readable. If this was going to be something you put in like a publication or something, I wouldn't have a legend at all. I'd probably label the lines, put a label right here at the start or at the end. Okay. So one last thing you might want to do with factors, if you subset your data, say with filter, on a factor and you drop some like 100% of the observations of a particular level, the factor keeps all those levels even if there's no longer any data that has those levels. These are called unused factor levels. If I say take my JZ data and then I filter so that track is only in I Just Wanna Love You and Big Pimpin'. So this is only now these 2 tracks in the song. But if I get the levels of track in this thing, you'll see even though the only songs represented are these 2, it still has all 5 of the original songs listed as levels. They don't actually exist in the data, but the factor preserves them as potential levels. If you want to get rid of these levels, you can say, take the entire data frame and then drop levels. You'll notice this is not a mutate command. This actually drops all of the unused factor levels in every variable in your entire data set. It's a base R function for doing it. If I get the levels of JZ's biggest, it now only shows the factor levels represented in the data. If you leave these factor levels in like this and plot a ggplot, sometimes it will just have empty slots in the ggplot with no observations, but they'll be there because the factor levels are there. Not always, it depends on which geom you use. Okay. Is dot required because it's a base function? No, I think you could actually remove the dot. It would still be there, but I reflexively put it there because I think it's a good habit. Okay, so the homework for this week is a little bit different from past ones. It is template-based again, but it's a little bit more free form than the last homework. So the idea here is that vote tallies, you're going to work with vote tallies from King County's 2016 general election. It's a 60 megabyte comma delimited text file. At least I think it's comma delimited and not TSV. I forget. They can be found on the course website. The data have very little documentation. All you've got is what's provided in the template. So you want to show a little bit of detective work answering questions about the data, cleaning them up using the template. You'll have to download the data manually, both the template and the data from the website, and open them up. This homework is broken into 2 parts. You'll complete the first part for this coming week, and then the second part for the week after. I say it's a daunting homework. It's pretty long, but it's broken up into 2 pieces. I say take a look at it before we have lab on Monday. If it's just overwhelming, come to lab on Monday. We will walk through it, and you'll find it's pretty fast to walk through it in lab, but it might be nice to struggle against it just a little bit to get a feel for working with real data. And when I say real data, they suck. This is a terrible data set. It's an administrative data set of the kind you normally would pull off a government website, which means it's terrible. It's god awful. The data format doesn't make any sense. It's barely even human readable. It's nice to work with these things because if you can master working with a data set like this, you can work with most social science data sets without too much problem. Okay, ask questions on Slack, email, all that kind of thing. We'll work through it carefully on lab. If you got any questions, hit me up.
Do you have a moment for a verbal question, or are you running off to the next thing?
You got me.
Okay. I had a question about date time data since I'm dealing with it for potential thesis work. I've been advised before that if you have a date and time, you want to leave them together instead of having them separate.
Mm-hmm.
One of the technical challenges we're running into is we recorded everything in Access, and in some instances, we're missing times. Like we have a date that the event's going to occur, but not the time.
Yeah.
And depending on how that was entered into the spreadsheet, sometimes it exports as, and depending on Excel's formatting when you export it, it'll show up as either just no date at all, which is manageable, or it'll autofill midnight.
Yeah.
And so I'm wondering, like, if you were designing a questionnaire or a data instrument, how would you go about setting it up for success later?
So it kind of depends. Well, I mean, if I'm setting something up, the first thing is to make sure that like dates and times are, well, what is the date and time of?
It's the date and time that somebody conducted an interview.
Okay, but it's not automatically collected. They have to write it in.
Yeah, it's a hand paper forms that are then put into the database, and it's multiple different data collectors.
Okay, so it kind of depends to some degree whether the time information matters at all. It might be the case that it doesn't really matter too much, but normally what I would do is I would probably still store it as, I'd probably store the overall date time column, like one date time column, and then a second column that indicates when the time data is wrong or missing. So you have a flag column.
Gotcha.
That would be the way I've done it in past like survey data sets. I usually like, I kind of manage the Denver Youth Survey a little bit. And with Denver Youth Survey, many columns in the data set have a redundant second column. That's a flag column that indicates reasons to interpret differently values in the main column. So it'll have like a set of factor. It'll be like a factor one that has like 12 levels. And some of them are like, okay, these data are unreliable for this reason, they're missing and why they're missing, that sort of thing. That's a good way to do it. Another thing you could do is you could split it into different date and time columns, which is perfectly valid. I would keep the original date time column, but there's no reason not to split them. It doesn't really hurt.
But you're thinking when you record it initially, keep them together so that you don't end up with accidents.
Yeah, I mean, it doesn't really matter too much. It depends how the data are being like entered. Because I mean, this really comes down to how do people conveniently like enter the data. If they're tabulating, like they're filling in like a Google sheet or something, you know, it could be one field, it could be multiple fields, it doesn't really matter. I don't know if you're being systematically, it's hard to know what would induce more data input error. I'd almost rather have separate fields because I think people are less likely to fuck up the date than the time.
Yeah, I think we probably should have done that.
Yeah.
You know, and then the sort of corollary to that is dealing with time zones. Once you're, because at some point when you're using an RE, you're using that POSIX format. And,
yeah. It depends whether it's meaningful, if the time zone is meaningful or not.
It's totally not. What we're doing is just we're measuring differences, basically like time from one event to another event. It's all in the same time zone. Like the time zone data is totally redundant. And in fact, can get in the way when you're doing some of the transformations. So would you just like time zone everything as UTC?
Yeah.
Or can you strip it out in any way, or is that a bad idea?
Well, you can't really strip out the time zone because there's always an implicit time zone. Because it's the POSIX time is it implicitly has a time zone because it's counting from January 1st, 1970, which means it always has a reference because what January 1st, 1970 happened at different times in different places. So time is always in reference to something, and so you kind of have to have a time zone. So by default, it's UTC, but you know, use whatever. I usually default to Pacific Standard Time because most of my times are that, but it doesn't really matter, you know.
Okay, but just like pick one, stay consistent.
Yep, stay consistent.
Okay, that's handy. Thank you. I noticed that there's one other person still on. Do they have a question as well?
Yeah, I just have a quick question that's much simpler.
Okay.
I just wanted to review again in the pivot longer. So I'm a little confused when you say, like, I understand that you're trying to make your data longer as opposed to wider, but like, I'm confused about the names too and values too. Like I know that it says you want to take week and rank and turn those into 2 columns, but I don't get like what the name to and values to does.
Values. Oh, okay. So might be easy if I just demonstrate. Let's okay. Need my Billboard data. Where are you at? Okay, so my Billboard 2000 raw look like this. So the initial data are like 1 row per artist's song, right? And then a terrible 76 columns of ranks, of which almost all of this is missing, right? So what I want is I instead want 2 columns. I want one column that indicates the week, which is up here in the column names, and another one that indicates the actual rank it was in that particular week. To do that, I'm going to say we're going to create a new column called week and a new column called rank. If I do that, I end up with a new column called week, a new column called rank, and this contains the week that it originally was. If I look back to my raw data, so for this Tupac song, Baby Don't Cry, in week 1, it was rank 87, in week 2, it was 82, in week 3, it was 72, right? In my new data, week 1 is 87, week 2 is 82, week 3 is 72. So what the pivot longer has done is it's taken all of these column names, put them into a week column by saying names to means the names of the old columns will go to a week column. The values that were in those columns will go to a rank column. So now I have week and I got rank.
Okay, so it's taking the like ranks from the essentially, and it knows that because you have starts with WK to like concatenate all those kind of.
Yeah, so starts with WK says grab every single column that begins with WK, and all of them are going to get pivoted down. And so it just grabs all the columns, stuffs them all in here. And what it's going to do is it's going to, so you'll see this is like week 1, rank 87. If I get all the way to the end of this song,
Then it'll
it's gonna
go to,
repeat,
yeah.
right? And then every single track here is just repeats week 1 through 76. You see most of them are missing data, right? Which we dropped later, but it just grabs all the columns. And so you can think about what it's really doing. It's like, you can see me, but it's taking like all these columns and it's actually pivoting them down. It's like flipping them down. It's actually rotating the data. That's all it's doing.
Okay. Okay, thank you.
Yep.